Hello all, this is the first lecture for the discrete or digital control system. We will revise Z-transform. Z-transform is an important tool in the analysis and design of discrete time systems. It simplifies the solution of discrete time problems by converting line time invariant difference equations to algebraic equations and convolution to multiplication. Because we primarily interested in application to digital control, this brief introduces the Z-transform in restricted casual signals with zero values for negative time and one-side Z-transform. We have this discrete time system. The system having is U with time. We have samples at sampling time equal t. We have the discrete time equals u0 times delta of t, u1 times delta of t shifted by t capital, t minus t capital, and u2 times delta times t minus 2t, and u3 times delta of t minus 3t. We have u hat or u star equals the summation k equals 0 to infinity uk times delta of t minus kt. D is the sampling time. We have f of t. Taking the Laplace transform, we get f of s. And f of t minus t naught, we take the Laplace equals f of s times e power negative s t naught. The impulse Laplace transform equals 1. And for the impulse shifted by time t will be 1 times e power negative ts. Impulse shifted by 2t equals 1 minus times e power negative 2ts. Then the general form delta of t minus kt having the plus equals 1 minus e power negative kts. The Laplace transform of the discrete u of t, which is u star of s, equals u naught plus u1 times e power negative ts, u2 times e power negative 2ts, u3 times e power negative 3ts, and so on. Then we have in the summation form, summation k equals 0 to infinity, uk e power negative kts. Over uk times e power negative ts power k, e power negative ts, which will define z inverse, z power negative 1, which is a time delay operator. Then the casual sequence is u0, u1, u2 until uk. Its z transform is defined as u0 z power 0, u1 z power negative 1, u2 z power negative 2 plus u3 z power negative 3, which is in the summation form, summation k equals 0 to infinity, uk z the power negative k, and uk means u of u subscript k equals u of k. The z transform applies to continuous time signal x of t, sample time signal x of kt, and the number response x of k. In one-sided z transform, we assume that x of t equals 0 for t smaller than 0, or x of k equals 0 for k smaller than 0. Then we will now discuss z transform. We need to obtain z transform of a unit step function. For a unit step function, all the samples are equal to 1 from 0, 1, 2, 3, and so on and so forth. And before 0, it is time 0 it will be equal to 0. Then we have sigma k equals 0, f of k, z power negative k, which is equal to 1, z power negative 1, 1 times z power negative 1, 1 times z power negative 2, 1 times z power negative 3, which is equal to the Maclaurin expansion of 1 over 1 minus z, or 1 over 1 minus z power negative 1. We multiply the numerator and denominator by z, which is equal z to divided by z plus 1, which is the z transform of the unit step function. For a unit step function, the Laplace of it was 1 over s, and for a unit step, f of z equals z over z minus 1. The integrator in the s domain was 1 over s. for the integrator in the z domain or the discrete time domain equals z over z minus 1. Both Laplace and Z transform represent either a signal or a system. It can be a signal or a system like the integrator. Now we will discuss the impulse, the unit impulse. We have k summation k equals 0 to infinity delta of kt times z power negative k. We have only the signal at k equals 0 and 0 at any other k value. Then f of z will be equal to 1 for the discrete time of the impulse. If we have the exponential e power negative a kt, we get summation k equals 0 to infinity e power negative a kt times z power negative k. We get 1 plus e power negative at z power negative 1 e power negative 2 at z power negative 2 e power negative 3 at z power negative 3 and so on and so forth. We have 1 e power at negative 80 z power negative 1 e power negative 80 z power negative 1 all power 2 e power negative 80 z power negative 1 all power 3. This is the Maclaurin expansion of 1 minus e power negative a t z power negative 1 to the power negative 1, which is 1 over 1 minus e power negative at times z power negative 1. We multiply the numerator and denominator by z. We get f of z equals z divided by z minus e power negative at. For a constant to the power a power negative kt. We apply the same steps, summation k equals 0 to infinity, e power negative kt z power negative k. We get 1 plus e power negative t z power negative 1, e power negative 2 at z power negative 2, e power negative 3 at z power negative 3, and so on and so forth. We get all these to the power 1, power 2, power 3, which is the Maclaurin expansion of 1 minus e power negative t z power negative 1 power negative 1 equals 1 over 1 minus a power negative t z power negative 1 multiply numerator and denominator by z. We get z over z minus a power negative t. For the sinusoidal equation sine k omega t, we have a the sine function equals e power j k omega t minus e power negative j k omega t over 2j. We have 1 over 2j, and for the exponential we have discussed in the previous slides, z equal over z minus e power negative j omega t minus z over z minus e power negative j omega t. We multiply, get a common denominator, z minus e power j omega t times z minus e power negative j omega t, and for the numerator is z times z minus e power negative j omega t minus z times z minus e power j omega t. We multiply z by the bracket for this and for this. We get z square minus 2 minus z e power j negative j omega t minus z square. We cancel z square by negative z square plus z e power j omega t. Then we obtain z times e power j omega t minus e power negative j omega t divided by 2j over z square minus z times e power j omega t plus e power negative j omega t plus 1, which is z sine divided by z square minus 2z cosine plus 1. This is the final form for the sinusoidal function. For the cosine function, we apply the same steps, e power j k omega t minus e power negative j omega t k omega t over 2. We have half times the z transform of e power j k omega t and the z transform of e power negative j k omega t. We get the common denominator and we obtain the denominator. We have k square and k square, 2k z square, z square, z square, minus z or 2z square and the half cancelled with the 2. Also for negative z e power j negative j omega t and z e power negative j omega t, we have z common factor e power j omega t plus e power negative j omega t divided by 2. and the denominator is z square minus 2z times the bracket, the same bracket as the numerator plus 1. Then we substitute for the cosine z square minus z cosine omega t divided by z square minus 2z cosine omega t plus 1. For the ramp, ramp equals kt, k equals 0 to 1, 2, and so on and so forth. The z transform of it is f of kt z power negative k summation from k equals 0 to infinity. F of k is kt, then 0, and then at t equals 0, t times z power negative 1, 2 t times z power negative 2, 3 t times z power negative 3. Multiplying both sides by z power negative 1, then we have z power negative 1 f of z, t z power negative 2, 2 t z power negative 3, 3 t z power negative 4, and so on and so forth. Then we have 1 minus z power negative 1 times f of z equals t times z power negative 1 plus 2z power negative 2 plus 3z power negative 3 minus z square z power negative 2 z plus 2 z power negative 3 plus 3 z power negative 4. Then 1 minus z power negative 1 f of z equals t times the bracket z power negative 1 plus z power negative 2 plus z power negative 3 plus z power negative 4. Then we will have this value. The next step, we take z power negative 1, a common factor from the right side, z power 0, z power negative 1, z power negative 2, z power negative 3. Then we have z power 0, z power negative 1, z power negative 2, z power negative 3 is a Laplace of the unit step, which is equal to z over z minus 1. Z is cancelled with z power negative 1, then t is over z minus 1. We multiply both sides by this bracket, then t times 1 over z minus 1 times 1 minus z power negative 1, which is tz over z minus 1 square. Then f of z equals tz over z minus 1 square. This is a summary for z transform of elementary functions. The constant is equal to cz times divided by z plus minus 1, which is like the unit step. For the unit impulse, which is equal to 1, unit step u of t or u of kt equals z over z minus 1. The unit ramp equals 2z over z minus 1 square. Exponential z over z minus e power at sine omega t or sine omega kt equals z sine omega t divided by z square minus 2z cosine plus 1. For the cosine function, cosine omega t or omega kt, z square minus z cosine omega t divided by z square minus 2 z cosine omega t plus 1. The first property, if we multiply a function by a constant, then we multiply its z transform by the same constant. If we have z of 3k omega u of kt, then we get the Laplace of the unit step, which is z over z minus 1, and multiplied by the constant 3. The second property is the linearity. We have z of ax of kt plus or minus b of y of kt, the same as the above. We multiply x of z by a and add it to y of z times b at t equals 1. If we have this, we need to get the transform of 2 times impulse plus 3 times exponential plus 4. We get the impulse equal 1 and multiplied by 2, and get the exponential, which is z over z minus e power negative at, and multiplied by 3. And for the 4, we get the Laplace of 1, which is the constant 1, equals z over z minus 1, and multiplied by 4. For the third property, if you multiply a function by a to the power kt, then we divide, we get f of z divided by at. Then z of a power kt u of k equals the Laplace, the z transform of u of k, which is z over z minus 1, and then we substitute every z by z over a power t, z over a power t, we get multiply the numerator and denominator by a power t, then it will be z over z minus a power t. If we get z of e power a kt times f of kt, then multiplying exponential by a function, then we will get f of z over e power a t. E power z of e power a kt times u, we get z of u, which is z over z minus 1, and substitute every z by z over e power a t, and for the numerator the same. Then we multiply the numerator and denominator by e power a t, then we get z over z minus e power a t. If we have kt times f of kt, then this is will be the derivative d by dz of f of z multiplied by negative tz. If we have f of kt equals negative tz d by dz of t, which is z over z minus 1, negative tz, and we get the derivative of this, the denominator power 2, the z transform or the derivative of 1 of z equal 1 times z minus 1 minus the derivative of the numerator, which is 1 times z minus 1, we get tz divided by z minus 1 square. For the z transform, we need to get z transform of kt e power negative a kt. We get for t equal 1, we get tz d by dz of the exponential z transform z over z minus e power a negative a, which is equal to negative z, and we get the derivative of the fraction z minus e power negative a square, and the derivative of the numerator equal 1 multiplied by the denominator z minus e power negative a minus the denominator z minus e power negative at multiplied by the derivative of the numerator, which is equal to 1. We get the last part, z e power negative a divided by z minus e power negative a square. Then multiply or another solution, we can substitute have the equation kt and shifted by e power negative at, then we get its z transform negative tz divided by z minus 1 all square, and we substitute by every z with z over e power negative a as in this part, then multiply the numerator and denominator by e power negative a square, then we get z minus times e power negative a divided by z minus e power negative a all square. If we have x of s equals 1 over s times s plus 1, we get the partial fractions 1 over s plus negative 1 over s plus 1. The first one is a unit step minus exponential e power negative t. We got the discrete time u of kt minus e exponential for the u equals z over z minus 1, and for the exponential z over z minus e power negative t. The shifting theory, x of k minus n equals z power negative n times x of z, x of k plus n equals z power n x of z minus summation k equals 0 to n minus 1, xk z power n minus k. For the first order, x of k plus 1, we get z x of z minus x z x of naught. For x of k plus 2, z square x of z minus z square x of naught minus z x of 1. The proof for this property, and for the second one, the table for the z transform of x of k plus 4 equals z power 4 x of k of x of z minus z power 4 x of 0 minus z cube x of 1 minus z square x of 2 minus z x of 3. For x of k plus 3, z cube x of z minus z cube x of of a node minus z square x of 1 minus z x of 0 x of 2 z of k plus 2 z square x of k minus z square x of 0 minus z x of 1 x of k plus 1 z x of k x of z minus z x of 0 x of k equals x of z x of k minus 1 z power negative 1 x of k z x of k minus 2 z power negative 2 x of k z x of k minus 3 z power negative 3 x of z x of z of k minus 3 z power negative 4 x of z. For the initial and final value theories, x of 0 equals limit in s tends to infinity s x of s. The initial condition x of infinity equal limit in s tends to 0 s x of s. The final value or steady state. For the z domain, we have x of 0 limit when z tends to infinity x of z. The initial condition, the x of infinity limit when z tends to 1 z minus 1 times x of z, which is the final value or the steady state value. For this equation, get the final initial and final value for the function x of 0 limit on z tends to infinity x of z. We substitute by infinity for the numerator and denominator. We get infinity divided by infinity, which is undefined value. Then we divide both the numerator and the denominator by z square. We get 1 over z divided by 1 minus 0.7 z plus 0.1 z square. We substitute by by z equals infinity. We get 1 over infinity equals 0. And for the denominator equal 1. 0 divided by 1 equal 1. For the final value, we limit z tends to 1. Z minus 1 x of z. We get the final value. Limit when z tends to 1 z minus 1 times z over z minus 0.2 times z minus 0.5 equals 0. The final value is equal to 0. Also get the z or initial and final value for this value. We have limit when z tends to infinity x of z, which is initial value. Limit when z tends to infinity z over z squared minus 1.5 z plus 0.5, which is infinity divided by infinity. By dividing both the numerator and denominator by z squared, we get 1 over z over 1 minus 1.5 over z plus 0.5 over z squared, which we substitute by infinity. 1 over infinity equals 0, and for the denominator we're equal to 1. Limit when z tends to 1 z minus 1 x of z. The final value or the steady state. Limit when z tends to 1 z minus 1 multiplied by the function z minus 1 is cancelled with z minus 1. We substitute by 1 over 1 minus half equals 1 over half equals 2. The final value will be equal to. Another example, find the initial and final values for the following function: z times 1 minus e power negative t divided by z minus 1 times z minus e power negative t. For the initial value, limit when z tends to infinity x of z. We substitute limit when tends to infinity z times 1 minus e power negative t divided by z squared minus z e power negative t minus z minus e power negative t. We substitute by z equal infinity. We get infinity divided by infinity. Then we divide both the numerator and denominator by z squared. We get 1 over z minus e power negative t divided by 1 minus e power negative t minus over z minus 1 over z minus e power t over z squared. We substitute by z equal infinity. We get 0 over 1. And for the final value, we get limit z tends to 1 z minus 1 x of z, the final value or the steady state of the system. We substitute z minus 1 and is cancelled with z minus 1 and substitute by z equal 1. We get 1 minus e power negative t divided by 1 minus e power negative t, which is equal to 1. Summary of Z transform properties. First, the linearity property. If a function is multiplied by a and added to another function multiplied by b, then we get the Z transform as first function multiplied by a and Z transform as the second function and multiplied by b. The scaling, if we scale a function by a to the power t, then we will get the f of z divided by a power t, or we substitute the f of z by substitute every z in f of z by z over a power t. Complex translation, if we multiply by exponential e power negative t f of t, then we get f of e power a t times z. Multiplying by t in the time domain t f of t, then we have derivative d by dz f of z and multiply by negative tz, shifting to the right, f of t minus nt equals z power negative n f of z, and shifting to the left, f of t plus nt, we get z power n f of z minus summation from m equals 0 to n minus 1 f of mt z power n minus m. Now we have finished the revision for Z transform. See you in the next lecture.